Now that we know what the general structure of the collection of solutions for higher order linear equations looks like, we kind of have a plan for how to go about solving them. It does kind of depend on whether your equation is homogeneous or non-homogeneous. So for homogeneous equations, we found that we're going to concentrate on second order differential equations here. So for a homogeneous equation, if we can just find two linearly independent solutions, y1 and y2, that form a fundamental set, then we can just write down the general solution, which is c1y1 plus c2y2. So we just have these arbitrary constants that combine our fundamental set of solutions. And these constants in general are going to be determined by any initial conditions we happen to have. For non-homogeneous equations, it's a little more complicated. We do still have to find a fundamental set of solutions, but it's a fundamental set of solutions for the associated homogeneous equation. And then also we have to find one single solution, called a particular solution, to the original differential equation, the non-homogeneous linear differential equation. And then we can write down the general solution, which is the particular solution plus the so-called complementary function, which is just the general solution for the associated homogeneous equation. So that's the plan. You can see for whether the equation is homogeneous or non-homogeneous, we do have to solve some homogeneous equation, whether it's the original homogeneous equation or the associated homogeneous equation. So let's concentrate for a second on finding solutions to a homogeneous linear second order differential equation. Now we have to find two, so what we might do to get ourselves started is just suppose we know one solution and see if we can use that to find the second solution. So here's an example. So y double prime plus 2y prime plus y equals 0, and this has as a solution e to the minus x, so you can check that if you want. So let's see what else we need to write a general solution for this equation. Well, based on our plan from the last slide, what we need is just one more linearly independent solution, y2. And since we don't really have general techniques for finding solutions to a differential equation, we kind of have to make a guess. And one way of guessing is, if we already know one solution, it seems like we should somehow try to use that first solution to make a good guess for a solution. So rather than guessing just a particular formula for some function of x to put over here, what we're going to do is say, well, maybe our second solution should be our first solution, but multiplied by some function of x. So this is going to be our guess, that our second solution is some unknown function u of x times y sub 1, but then we're going to try to find this unknown function u of x. So this is, y1 is e to the minus x. So we have e to the minus x times u, and we need to find u. But, what do we know about u? Well, this y sub 2 is supposed to be a solution to the differential equation. So that means we could plug this into the differential equation. And that would give us some other equation that maybe will tell us what u is. So let's try to plug y sub 2 into this differential equation. So we're going to have to start by computing some derivatives. And keep in mind as we compute these derivatives that u is really a function of x. So there's a product of two functions of x here, so we're going to have to use the product rule. So y sub 2 prime is, minus e to the minus x times u plus, and now the second part of the product rule, e to the minus x times u prime. So there's the first derivative. Now for the second derivative of y sub 2, we get, so again we have to do the product rule on each piece here. So we get, on the first piece, when we do the first part of the product rule, the chain rule spits out a minus sign, so we get e to the minus x times u minus e to the minus x times u prime. So that's the product rule on this first term. And now we do the product rule on the second term. We get minus e to the minus x times u prime plus e to the minus x times u double prime. We can simplify this. Those middle two terms we can simplify. So e to the minus x times u minus 2e to the minus x times u prime plus e to the minus x times u double prime. Okay, so now that we know y sub 2 prime, and y sub 2 double prime, we can put all of these into the original differential equation to see if it tells us something about u. So we get, let's see, it was y double prime, which is e to the minus x times u minus 2e to the minus x times u prime plus e to the minus x times u double prime. So that was all y double prime plus 2 times y prime, I think. Yes. So plus 2 times, and then y sub 2 prime is minus e to the minus x times u plus e to the minus x times u prime plus y, and y sub 2 is e to the minus x times u, and this is all supposed to be equal to 0. Let me just double check that I copied that right. Yes. Okay, so it's hard to know what this tells us about x, but clearly we should, hard to know what this tells us about u, but clearly we should simplify this because there's kind of a lot of stuff all over the place. So let's see. We have, let's gather up all the e to the, let's gather up all the u terms. So here we have a u term, here we have a u term, and here we have a u term. So e to the minus x times u minus 2e to the minus x times u plus e to the minus x times u. Okay, now let's write down all of the u prime terms. So there's one here and there's one there. So this is, let's see, minus 2e to the minus x times u prime. That's the first one. And then the second one is plus 2e to the minus x times u prime. And then finally, we have a e to the, a u double prime term. So plus e to the minus x times u double prime. Okay, now as I was writing this all out, you probably noticed that a lot of this simplifies. So all of this stuff here, all of our u terms actually add up to 0. And then also it looks like our u prime terms also add up to 0. And so we're left with e to the minus x times u double prime equals 0. And so we can remember what we were looking for was an equation that will tell us what u is. And this equation does tell us what u is because, look, we can divide both sides by e to the minus x. We get u double prime equals 0. Right? It's safe to divide by e to the minus x because e to the minus x is never 0. And now we can take two integrals to find u. So integrate once, you get u prime as a constant. Integrate again, and we get that u is some constant times t plus some other constant. All right, and so y1, our first solution, was e to the minus x. So our second solution, y2, we guessed that it was u times our first solution, and now we know what u is. Oh, I wrote t, this should be an x. Now we can put in what we found for u. So our second solution is some constant times x plus some other constant times e to the minus x. Now, remember, all we're really after is some second solution that is linearly independent from e to the minus x. And if you think about d times e to the minus x, this isn't linearly independent from e to the minus x. So let's just throw that term away, right? These constants could be anything. So we can pick values that give us what we want, and we want an independent solution, a linearly independent solution. So let's discard this D part, and we could choose anything for C that we want other than 0, so let's just choose 1 for C. So that gives us a second solution, x times e to the minus x. Now, I won't double check that these really are linearly independent, but if you compute the Wronskian of these two, you will find that the Wronskian is non-zero, and so these two functions are linearly independent. So now that we have two linearly independent solutions to the differential equation, right, we have a fundamental set of solutions, so we can write the general equation, or I'm sorry, the general solution to the differential equation, which was y double prime plus 2y prime plus y equals 0. So the general solution is y is an arbitrary constant times y sub 1, which is e to the minus x, plus another arbitrary constant times our second solution, x e to the minus x. And so there's our general solution. By all of our uniqueness theorems for higher order linear equations, we know that all solutions will take this form.